Suppose that Roger lives in London, and he wants to visit his friend Casper who lives in Munich. Roger wants to take the train to Munich, so he looks for a train map on the internet. He finds a website called LW Navi, which displays the following train map. Roger cannot figure out how to get to Munich, so he asks LW Navi to calculate the shortest route from London to Munich. After a few seconds, LW Navi shows us the route to Munich that takes the shortest amount of time. In addition, LW Navi tells us the shortest distance route and the least expensive route. We take navigation apps for granted, but they are remarkable pieces of engineering. How does a computer, or a set of computers, calculate the route from every train station to another in just a few seconds? In short, computers act much like humans. The computer reads a map, and it constructs some routes from the origin to the destination and compares them. But while humans use 2D image maps, computers use a graph. Here's an example. The vertices represent train station locations. An edge between the two vertices indicate that the train stations are connected by rail. Edges have a number, or weight, that represents the distance between the connected train stations. Before we discuss route computation, let's first describe graphs more precisely by converting the diagram into a collection. Note that our description is just one of many different ways to define a graph. An edge consists of two nodes that the edge connects and the edge weight. For example, edge London, Paris 5 describes an edge that connects the nodes London and Paris and has weight 5. A graph is just a collection of edges. For example, consider this simple graph. The collection representation of this graph is edge London, Paris 3 and edge London, Amsterdam 4. The stack contains two elements and each element is an edge. Here's a graph with more cities and the same graph as a stack. And here's the same graph as a table. By inspecting this graph, we can see that Paris is 8 units away from Barcelona, for example. Next, let's examine some things we can do with graphs. Suppose Melissa lives in Brussels. Let's get the list of all the cities Melissa can reach non-stop. Our strategy is to inspect the edges one by one. If one of the two nodes in the edge is Brussels, the other node is directly reachable, so add the other node to the result. Here is the procedure in tabular form. We start with the top element in the stack, which is the edge London, Paris 3. This edge does not contain Brussels, so it is not added to the result. Next we have edge London, Amsterdam 4. This also does not contain Brussels. Then we have edge Paris, Brussels 3. This edge does contain Brussels, so we're going to add the other node, Paris, into the result. Next we have Paris, Barcelona 8, which does not contain Brussels. Then we have Paris, Milan, which also does not contain Brussels. Then we have edge Brussels, Amsterdam 3. This edge does contain Brussels, so we're going to add the other node, Amsterdam, into the result. Next we have edge Brussels, Munich. This one also contains Brussels, so we're going to add the other node, Munich, into the result. The last two edges do not contain Brussels, so we skip them. Thus, the cities that are directly reachable from Brussels are Paris, Amsterdam, and Munich.